Chapter 5 is a pretty short one. There's just 3 sections that we're going to do in section 5. We'll have this all wrapped up before you head home for break in a few weeks. Today we're going to take care of section 1. Section 1 is all going to revolve around one theorem, which makes things a little bit easier. So really just one main thing you got to remember here from this section. And there is a proof that goes with it. The proof will be on the test. I'm going to save that for the end after we do our examples. The proof really isn't all that complicated. It's going to look a lot like what you did last chapter with proofs. Now, the first thing we need is a definition of perpendicular bisector. And I don't remember if we've talked about this year already or not. We might have talked about perpendicular bisectors. But even if we haven't, we can kind of put together what's going to be happening here. We know these two words, perpendicular and bisector. Perpendicular, when you have perpendicular lines, what happens where they intersect? They're going to make right angles. So perpendicular is going to give us right angles. And then you have a bisector. What's a bisector do? Cuts it in half. So we're going to split something in half. The thing we're going to cut in half is a segment. So the perpendicular bisector, our definition, it's going to be either a segment, could be a line, could be a ray, could be a bunch of different things. And it's going to do two things. It's going to be perpendicular to a segment. That's going to take care of the perpendicular part. It's going to be perpendicular to the segment. That's going to give us right angles. And then the bisector part of it means it's going to split it in half. So it's going to intersect at its midpoint. Let's draw a picture of what that's going to look like. You're going to have a segment line or something like that that's going to be perpendicular to a segment that intersected and intersects it at its midpoint. So let's start with a segment. I'm going to call the segment AB. This is going to be the segment that gets cut in half. So what we need is another line, segment, ray, something like that. I'm going to do a line. We're going to have a line that's going to intersect this one. And when it comes down here through this segment, to be a perpendicular bisector, the first part it's going to do is make right angles. It's going to be perpendicular, so you're going to get right angles here. And then the other thing it's going to do, it's going to intersect that segment at its midpoint. So this point right here is going to become the midpoint. That's going to make these two segments congruent. Just to give them some letters here, let's make that midpoint, we'll call that M. And this line we drew in here that ends up becoming the perpendicular bisector, let's call that L. So in this picture right here, L is a perpendicular bisector. And when we get into the proof we're going to do with this section here, that perpendicular bisector, we're going to have to make sure we do both parts of it. The perpendicular part gives you the right angles. The bisector part splits the segment in half. So we'll keep that in mind as we get to the proof. There's going to be two parts when we do the perpendicular bisector. All right, here is the theorem that we have to remember with this one. It's called the perpendicular bisector theorem. I'm going to read this one to you in words first, and then we'll draw a picture of it. When you first hear the words, it's probably not going to make a whole lot of sense to you. But when you see a picture of it, it will. Here it is in words. Perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. Here's what that means. Let's start with our segment once again. I'm going to call it AB again. And then just like we did before, we're going to have a perpendicular bisector. So we need a line coming through here. That's going to form right angles, split the segment in half. Let's make this midpoint here D. So there's the picture we need. We've got our segment. We have a perpendicular bisector coming through it that gives us right angles and splits the segment in half. Now, the theorem says if you pick any point on that perpendicular bisector, here's the perpendicular bisector. I could pick a point on top, on the bottom, in the middle, it doesn't matter where. I'm going to pick a point up here on the top. I'm going to call this point C. It says that point on the perpendicular bisector is going to be equidistant from the endpoints of the segment. Equidistant means it's going to have equal distance. So we're going to have an equal distance to both endpoints on the segment. So from point C, if I go to this endpoint here, point A, and I go to this endpoint over here, point B, those are going to be equidistant. That means they're going to be the same. Same distance between those two. And that's how that theorem is going to work there. If you see, you've got a triangle where you have that perpendicular bisector drawn in there, you get right angles here, and the bottom is split in half. Then the hypotenuse of each of those triangles is going to be congruent also. Now, when we do our proof, we're going to prove this, and the reason this works is these two little triangles end up being congruent by side angle side. And once the triangles are congruent by side angle side, then the corresponding parts are congruent by CP. So that's why that proof we're going to do is going to look a lot like what you did last chapter. So there's the first way you'll see it. If you notice the perpendicular bisector in there, you've got right angles and you've got the side split in half. Then the hypotenuse of each triangle will also be congruent. Now we're also going to do the converse of this because you're going to see it both ways. Once again, I'm going to read the words to you and then we'll draw a picture of it. The converse of the perpendicular bisector theorem says if a point is equidistant from the endpoints of a segment, then it is on the perpendicular bisector of the segment. So with this one, we're going to start with, well, let's just do it the same way. We'll start with our segment. I'll call it AB again. And now we're going to kind of do this backwards. Now we're going to have a point, which I'm going to call C once again. It's going to be equidistant from these endpoints. So now we're starting this way. So if that happens, where point C ends up being equidistant from the endpoints of that segment, then what we know is that point C is on the perpendicular bisector. So if I draw my line coming through here, the same thing's going to happen. We're going to get right angles down here, and we're going to split this side in half. So it's going to work both ways. We'll show you some examples here in a second so you can see how it works. But the main thing to remember here is if you see that perpendicular bisector, you get those right angles, and these two parts are congruent, that's going to make the hypotenuse congruent. And it also works backwards. If the hypotenuse of each triangle is congruent, then that means this thing here is going to be a perpendicular bisector. So you're going to get the right angles and you're going to get those two parts congruent. All right, before we go on to the examples, any questions with those two? Okay, let's show you how this is going to look. start with this first one. They're going to tell us to find AB on this one. That means they want us to find the length of AB. In our picture, we're going to start with a triangle. Start with triangle ABC. Oh, whoops, that's going to be ABD. And then on this one, they're going to draw in the perpendicular bisector. When we draw in that perpendicular bisector, we're going to get right angles here, and we're going to split the bottom side in half. And that midpoint there we're going to call C. And then the only other thing they're going to give us on here is they're going to tell us that the length of AB is 8. From that, we can figure out what the length of AB is going to be. AB is over here. So it goes back to our perpendicular bisector theorem. When we drew in this perpendicular bisector, we got right angles here, and this side was split in half. And our theorem says if you have a point, point A is on that perpendicular bisector, then it's going to be equidistant from the endpoints. The endpoints will be D and B. So if AD ends up being a length of 8, what's AB going to have to be? 8. That's all you have to do. AB is going to be 8. So really with these, you can just kind of look at the picture, come up with your answer pretty quickly. Now let's do one backwards. Let's say they tell us to find WY. And we're going to start with the triangle again. Top of the triangle is going to be X. The other two side or the other two vertices are W and Z. But this time we're going to do it backwards. This time they're going to tell us that WX is 9 and XZ is 9. Those two are both the same length. And then they're going to draw a line coming down through the top of the triangle. It's going to form a right angle here. It's going to hit at point Y. And the other thing they're going to give us here is that the length of YZ is 3. Here's the other way this will show up on the homework. This time, you've got these two sides congruent to each other. The hypotenuse of each triangle is congruent. That means that point X is equidistant from the two endpoints, W and Z. So if X is equidistant from the two endpoints, that means X is on the perpendicular bisector. And if this thing becomes a perpendicular bisector, you're going to get right angles, which we have here. And it's going to split that side in half. So if YZ is 3, what's WY going to have to be? So when they just put numbers on there like this, it's really just a matter of looking at the picture and get right to your answer. Now, the other way they're going to do this is they're going to make you do some algebra. And this really isn't any more complicated. It's just going to add another step. This time they're going to tell us to find RT. And this time we're going to switch our triangle. We're going to put it on its side. This triangle, we're going to have R over here on the right, and then Q and T are the vertices on the left. And this one, we're going to draw in the perpendicular bisector. So it's going to come through the top here. Be a perpendicular bisector. We're going to get right angles down here. Most of the time, the book will just draw in one right triangle or one right triangle here for one right angle in here. If you need to put the other one in, you can. That's totally up to you. And if it's a perpendicular bisector, it's going to split this side in half. This midpoint here, we're going to call S. And then the difference with this one, instead of just giving you numbers, they're going to give you expressions. So this side here is going to be 2x plus 3. This side is going to be 4x minus 7. doing what we did before. We said on our perpendicular bisector theorem, if you have a perpendicular bisector coming through your triangle, give you right angles here, split this side in half. When that happens, what do we know about each hypotenuse on the triangle? They're congruent to each other. So 2x plus 3, 4x minus 7, they'd be congruent. Solve that, and just put them equal to each other. Then we could solve it. If you subtract 2x from both sides, we get 2x over here. If we add the 7 to this side, we'll get 10. 10 divided by 2 is 5. So x is 5. We found our answer. Are we finished? Nope. What do they want us to find? RT. So you got to put that 5 back into RT. Here's RT right here. The 5 is going to go back into RT. When we do that, we're going to put 5 in for x. 4 times 5 minus 7. Okay. 4 times 5 is 20. 20 minus 7 is 13. So the answer they want is 13. So you have to be careful of that when you're doing these. Just make sure you're answering the right question. If you find x, make sure that they make sure you're asking. Make sure you're looking to see if they're asking for x or if they want to side. Okay, does anybody need to see another one like this? Okay, there's one other example I want to show you, because sometimes they'll try to trick you. On this one, they're going to tell us to find AC. And we'll go back to our triangle being straight up and down like we're used to. All right, we're going to draw this coming through the middle. Point D up at the top. And C are going to be our vertices, and this middle point here is going to be B. And this time around, they're going to tell us, we're going to kind of do this one backwards. AD is going to be 8, and DC is going to be 8. And we're going to get a right angle down here at point B. And the other thing they're going to give us is that BC is 2. Okay, this one's just numbers, so we can get to our answer pretty quickly. If these two sides are both the same length, these are both 8, that means D is equidistant from the two endpoints. If that's equidistant from the two endpoints, that means that D sits on your perpendicular bisector. So when we come down here, we're going to get right angles, and we're going to split this side in half. So if BC is 2, what's AB got to be? 2. AB is going to be 2. And then a lot of people will just leave their answer as 2, but is that what they asked us for? Did they want the length of AB? No, they want AC. If AC is this entire length, what's it going to be? 4 plus 2. So this one you got to be careful on. Sometimes you'll find that missing part, but they're not asking for the missing part. They want the whole thing. So you really got to follow directions on these to make sure you're answering the right question. Okay. That's all the examples I have for you. Does anybody need to see more examples? Good with those. All right, let's go to your proof. Would it scare you if I said the proof is 9 steps? 9 steps.
On the test, is it fill in the blank?
No.
No. Wait, no.
It's not fill in the blank. All right, here's the proof you're going to have to be able to do on the test. Sounds scary because it's got 9 steps. It's actually something you've basically already done last chapter. We're going to prove our perpendicular bisector. So for a picture, let's get a triangle over here. We're going to label the vertices A, B, and C. And then we're going to bring a segment straight down from point C to segment AB. It's going to hit over here at point D. And our given, we're going to be given one thing here. They're going to tell us that CD is a perpendicular bisector of segment AB. before we go any further on that, when you look at that, you see the word perpendicular bisector in your given. And a perpendicular bisector is going to do two things. Perpendicular part is going to give us right angles. Bisector part is going to split the side in half. So when we go to this proof, when we do the perpendicular bisector part, we have to do both parts. We got to show that we have 90-degree angles. We got to show that these parts, these two sides are splitting in half. Okay, and then your perpendicular bisector theorem says if CD is the perpendicular bisector, then these two sides over here, CA and CB, are going to be congruent. That point C is going to be equidistant from the endpoints A and B. So that's what we're going to prove here, is that AC is equal to BC. And then on your test, you're going to have to do this all by yourself, no help. All we're going to do is give you the picture, the given, and the proof statements. You got to come up with all the statements, all of the reasons. All right, now there is 9 steps to this one, but some of them we're going to know going off right off the bat here. When you look at your picture, going back to what we did last chapter, when you look at the picture here, there's 2 things you always want to look for in the picture. Do you have vertical angles?
No.
No vertical angles here. How about a shared side?
Yes.
Yes, they do have a CD shared by both triangles. So reflexive is going to be one of our steps. We know that going into it. Then go to your given. In the given, do you have a vocabulary word?
Yeah.
Yes, perpendicular bisectors. We're going to use the definition of that in our proof. We're actually going to end up using that a few times. Then go to your proof statement. We're going to prove that AC is equal to BC. Are we going to finish with a 3-letter shortcut or CPCPC? CPCPC. And then what's the other step that shows up in every proof? So we know 4 things going into it. Now this definition of bisector, definition of perpendicular bisector, we're going to end up actually end up using that 3 different times. So we're going to have what is that, 6 things going in there. There we go. All right, let's take care of it. First step, no matter how difficult the proof is, you know your first step is going to be given. So put that in your first. CD is going to be the perpendicular bisector. Maybe. That is our given. Now, before I mark the picture, I have to explain what a perpendicular bisector is. A perpendicular bisector we know is going to do 2 things. What's the perpendicular part going to do? It's going to make right angles. How many right angles are we going to get here? 2. So we're actually going to make this be 2 steps. Although you could potentially make it just 1 step. But on the homework assignment you're going to do today, we've got it listed as 2 steps. So we're going to show we have 2 right angles. If CD is perpendicular to AB, that means where CD comes down here and hits AB, we're going to get 2 right angles. One of them is going to be here. That's going to be angle ADC. That's going to be a right angle. And the other one's going to be on the other side right here. That's angle BDC. It's going to be a right angle. Now, when you get to the test, end of this chapter, if you combine this into 1 step, that's fine with me. Your proof would then just be 8 steps. But like I said, on the homework assignment, we're going to give you here in a little bit. We've got 9 steps set up for you, so that's why I'm splitting it into 2. All right, both of this is coming from that definition of perpendicular bisector. Second, get caught up here before we go. Now, you're probably going to have to do this proof on Alex. So when we put this in here, definition of perpendicular bisector, we put the little boxes here to show we got right angles. We look at that and immediately we think they're congruent to each other. That's just kind of natural what we think. Doesn't Alex look at it that way?
No.
Nope. Alex wants you to say that they're congruent. So in step 4, we're going to have to say that those 2 right angles are congruent. Those 2 right angles are ADC and BDC. Those are going to be congruent to each other. Anybody remember from last chapter what the reason's going to be?
All right angles are congruent.
All right angles are congruent. That is a step on that Alex proof. You will have to put that in there. So might as well get used to putting that in there right away. So at this point in our proof, we've got two sets of, we've got a set of right angles here that are congruent to each other. So we have one set of corresponding parts congruent to each other. Now let's go to step 5. The other part of our definition of perpendicular bisector is the bisector part. We already did the perpendicular part. What's the bisector going to do to it? Cuts it in half. What's going to get cut in half in our picture? AB is going to get cut in half. So that means when this thing comes down here, it's going to split AB in half. That's going to make AD congruent to BD. Mark it there first, and then put that into my proof. And this, once again, is coming from your given. Perpendicular bisector was in your given. This is the definition of perpendicular bisector. We end up using that one 3 different times on this proof. All right, 5 steps into it. We still know 2 more of our steps. What do you think we should do next? Might as well do reflexive. We know what's in here. Reflexive, you got CD congruent to itself. Mark it there. Then put it in the proof. Cross off reflexive, we use that. Now look at your picture. Do we have enough to say the 2 triangles are congruent? Yes, we've got 3 sets of parts that are congruent. We got a set of right angles, we got a set of sides here, and we got the shared side right here. So at this point, I can say the 2 triangles are congruent by which 3-letter shortcut? Side angle side. The angle is in between the 2 sides. Side angle side for step 7. Then when you name your 2 congruent triangles, you can do it 3 different ways. I'm going to call the triangle on the left ACD. If I go in that order, then the triangle on the right, I would have to call BCD. Oh, my pen's dying. Okay, we're almost there. 2 steps to go. What do you think is going to be the next thing? CPCTC. Once we get the triangles congruent, then our corresponding parts are congruent. The parts we want to get congruent here, we talked about this earlier. Perpendicular bisector theorem says if it's a perpendicular bisector, then that C is going to be equidistant from A and B. So CA and CB are going to be congruent. Now the order they have it here is AC and BC. So step 8, say that AC is congruent to BC because they're corresponding parts. That's the CPCTC. And the only thing left to do, we have the parts being congruent to each other. They want us to prove that they're equal. In step 9, we can go from congruent to equal. Going back to the last chapter, anybody remember what allows us to go from congruent to equal?
Definition of congruent.
Definition of congruent. So even though it's a new proof from a new chapter, it's really the exact same thing you did last chapter here. Just proving the 2 triangles are congruent to each other by side angle side. And then your parts are congruent by CPCTC. A little bit longer proof than what you're used to, but it's really the exact same thing you did last chapter. Okay, there's your 9 steps. Any questions with that? With that, anybody want to do it again? Whoever wants to do it again. Okay, let me turn off the video here. Do your homework.